Welcome everyone to our webinar, Power Transmission and Data Centers, Economic and Social Benefits. This session is being recorded and we'll email out the link to all attendees when it's available. We will have time for questions at the end of the webinar, so please feel free to leave your questions in the chat, but we will be responding at the end of the presentations. So we'll get started with an introduction of our first speaker. Raj Rajan is currently Vice President of Project Development for Sioux Green, building a rail co-located weather-resilient inter-RTO HVDC power transmission link. Raj has 4 decades of experience in environmental stewardship related to production infrastructure and supply chains of utility, transportation, energetics, chemical, petroleum, tourism, food, beverage, and paper industries. He most recently served as the Global Technical Lead for Corporate Sustainability Strategy at Ecolab. He was appointed by 2 Minnesota governors as statewide business representative to the Clean Water Council, where he served for 8 years advising the legislature. Raj is a licensed professional engineer in multiple states, holds a master's degree in environmental engineering from Southern Illinois University, and a PhD in environmental engineering from the University of Massachusetts, and is a fellow of the Institute on the Environment at the University of Minnesota. He currently serves on these nonprofit boards: Climate Generation, Environmental Initiative, and Fresh Energy. Raj, the floor is yours, and I will pull up our slides here.
Thank you, Ethan.
Yep.
So if we jump to the next slide, we have an outline here. We will be dividing it up. I will get into the why and the what of the project itself. And then Dr. Loomis will get in and talk about the economic impacts, both of the transmission project itself and the generation that will be associated with it. And then I'll jump back in and specifically talk about the societal impacts on the delivery end of the power. And lastly, Chris will talk about the economic impact of all the additional economic activity associated with the power that will be delivered. So if you go to the next slide, really, why this project? So transmission, everybody's aware that we have a rather balkanized national electric grid. And transmission bottlenecks are limiting investment in new power production, particularly the low-cost production of wind and solar electricity. And it's preventing affordable power from reaching customers in load centers, causing congestion and the associated reduced return on investment on the generation projects, and also driving up wholesale electricity prices for the end user because of the congestion and curtailment that comes with it. And using eminent domain to take private productive agricultural land, whether it's farmland or ranch land, for building overhead transmission projects through greenfield corridors has triggered a lot of opposition across all the regions where there is an abundance of low-cost renewable resources. And this has become a significant impediment to developing new transmission projects. And of course, particularly when it comes to the question of interregional transmission or inter-RTO transmission, there's always the question of who pays for the transmission and how is the cost allocated. And the value proposition for the generating end of the transmission line is quite different from the value proposition for the receiving end of the power. And so that becomes even more challenging in interregional and inter-RTO transmission for RTOs to come to an agreement on how the cost will be allocated to their customer base. So of course, if you look at the national map of population centers, or which analogous to load centers, and look at where the power generation is, there's a huge gap in terms of distances. So if you go to the next slide, well, we show a couple of maps here on the right side. The top one is the wind resources, wind speed, and clearly all the way from West Texas through Oklahoma, all the way up to North Dakota is what we call what is often referred to as the Saudi Arabia of wind in North America, which is where all the low-cost wind generation is located, and the entire southwestern U.S., of course, is where a lot of the abundance of photovoltaic solar generation potential is. And then you saw in the previous slide where the power centers and load centers were, and what connects them is really transportation corridors. So if you look at generation resources for low-cost renewable, variable renewable electricity generation, and look at not just current load centers, but projected load centers for future load, which is what a lot of what we are going to talk about today is associated with. There is a big gap, and particularly between the Midwest, where a lot of the wind resources, low-cost wind resources are located, and the Mid-Atlantic and the Northeast, where a lot of the aggressive decarbonization goals are for the states, and a lot of the data center and other clean energy related demand for electricity exists. And existing transportation corridors, primarily Class 1 railroad corridors, are a great alternative to site these transmission projects to get around opposition by landowners for eminent domain authority, environmental concerns during operation like migratory bird corridors, and also view sheds. Rural view sheds are affected quite a bit by overhead transmission lines, which is also another objection. So if you go to the next slide, we'll talk about what is the Soo Green project itself. We are called Soo Green because we are primarily along the Soo line, which is Canadian Pacific Kansas City, or CPKC's the North America U.S. operations. And it's a 350-mile project that connects two strong grid connection points. It's a grid-tied transmission project as opposed to a node tied to specific wind farms or solar farms. We connect to a very strong connection point near Mason City in Iowa in MISO Zone 3 and deliver the power to ComEd territory, which is part of PJM in outside Plano, Illinois. The project has a capacity of 2,100 megawatt nameplate capacity, voltage class 525 kV, and it is symmetric bipole, so it has bidirectional power capability, of course, with all the market-driven power primarily flowing from north central Iowa into northern Illinois, with emergency power with a joint operating agreement between MISO and PJM, having the ability to flip and deliver that power to Iowa if needed in the event of an emergency like those polar vortices and other extreme weather events that we have had happening more frequently and more intensely over the past few years. It uses the latest and best-in-class voltage source conversion, multi-level modular HVDC technology. And the cables that will be used will be manufactured here in the US and South Carolina by Prysmian, and these are XLPE insulated and shielded submarine-grade HVDC cables. So if you go to the next slide, what are the project goals? We want to expand into regional transmission, particularly between the Midwest and the Mid-Atlantic Northeast, which has been identified by DOE as a region with the most significant interregional transmission needs or gaps between what's available and what's needed a couple of decades or so from now, and connect to significant points on the grid, so we don't have to worry about congestion locally that will reduce the power that's delivered, and deploying a link that is reliable in that using leverages all the advantages that HVDC links provide between regional transmission organizations, and also resilient in that it's extreme weather resilient. It's underground. It will not subject to all the extreme weather event related disruption. We will significantly enable increasing the renewable energy on the electric grid because if you look at the levelized cost of generation in north central Iowa, western Iowa, it's really wind power that's primarily driving the wholesale electricity cost down there. And We particularly focus on the economically disadvantaged rural communities and bringing workforce benefits to them, and have developed a model to implement this both in Iowa and Illinois. And ultimately, the idea here is to create a replicable and scalable model, because if you look at load generation and wind and solar power and load centers for most of the new demand that's going to come up, as I mentioned, there are 6 Class 1 railroads that can pretty much connect all those points. And of course, an alternative model is also a subset of this, which is co-location and highways, which would require a lot of regulatory changes in many states based on current statutes. If you go to the next slide, a status update, the project is 100% site control. We have power line agreements with all the railroads, and also for the using their right of way, being located in their right of way. And we also have a couple of places where, due to constructability, we're coming off the rail right of way and using highways, and we have DOT utility installation permits both in Iowa and Illinois for that. Environmental surveys have been completed. All underground utility surveys are completed, so we know what the clearances need to be with existing underground utilities, whether it's using horizontal directional drilling technology or jack and bore technologies. RTO interconnection process is well underway. We have queue positions both on the MISO side for generation and the PJM side for the injection. And we have a preliminary system upgrade cost, system impact studies, and they're consistent with the earlier estimates, so no sticker shocks or surprises there that often tend to be something that could potentially derail merchant transmission projects. Supply chain is secured. We have secured a manufacturing slot with Prysmian for the HVDC cable manufacturing. First time HVDC cable will be manufactured in the US, in South Carolina, in Abbeville. And we've also secured manufacturing slot with Siemens, which is, of course, overseas in Germany, for converter station components. If you go to the next slide, I will summarize overall what is the key idea takeaway of this project is to co-locate transmission in existing commercial corridors, transportation rights of way, in almost entirely railroad and with some highway, and to so that we can accelerate the development. There's too much of an on-ramp for the time it takes to develop transmission projects through greenfield sites that rely on eminent domain and significant landowner objection. We get around that. We minimize land impacts. And by using HVDC technology and burying it underground in a secure corridor, limited access corridor, we're able to enhance grid reliability, which is very critical for the new economy that needs to be powered with these renewables. I will hand this over to Dr. Loomis to talk about the economic impact of the project itself.
And I'll do an introduction of Dr. Loomis. Dr. Loomis is president of Strategic Economic Research. He is also Emeritus Professor of Economics at Illinois State University and co-founder of the Center for Renewable Energy. Dr. Loomis has over 20 years of experience in energy analysis and has performed economic development analyses at the county, region, state, and national levels for many different energy projects and associated supply chains. Dave?
Thank you. And thank you, Raj, for explaining the project so well. In my presentation, I'm going to talk about the economic impacts of the transmission line itself, both the construction impacts and the operations impacts. And I'll also describe the economic impacts of the generation that will be unleashed with having this new transmission capacity available. We are assuming that the new generation would be both wind and solar, and that those projects could not be built except for the additional transmission capacity that this project will bring because of the existing transmission constraints in the area that we're looking to locate this line. Next slide. We've already gone through my bio, so we can go on to the next slide. So our methodology, we're using IMPLAN to model the economic impacts. IMPLAN is used by thousands of economic development professionals. It's based on US data, looking at input-output analysis. How are different industries related in terms of supply chain to those different other industries, so that ultimately we get this multiplier effect of dollars moving throughout the economy. So it's used, and we use data specific to state of Iowa, state of Illinois, where the project's located, but we also looked at those national impacts because of the supply chain impacts. As Raj said, the South Carolina manufacturing plant, there's going to be jobs that are created or supported in South Carolina because of the manufacturing that's taken place there. So we want to take care to say what of this is going to be sourced in the US and what of it is going to be sourced internationally. Next slide. In addition, we're using the JEDI model. The JEDI model is sits basically on top of InPlan, so it's perfectly compatible. But what the JEDI model does is allow us to look at future projected costs of wind and solar, and then break that down into its different components in terms of the costs of turbines, installation costs, construction costs, balance of plant costs, and things like that. So JEDI provides a platform to do that in the absence of specific information from a specific developer for a particular project. Next slide. So when we're doing economic impact analysis, we're looking at those initial capital expenditures as well as those ongoing operational expenditures. And we want to take care to say how much of those expenditures are going to happen in the local region where the project's going in. We'll then look, in this case, at those state impacts for Illinois, state impacks for Iowa, and then we'll look at the non-regional expenditures. In this case, we're considering the whole US, so we want to look at those supply chain impacts, such as I mentioned in South Carolina. But we also want to take care to look at, say, converter stations that may be sourced from outside the United States, and other materials. More and more, we're lots of initiatives to onshore a lot of the manufacturing capacity that has not been available. For example, jump the gun a little bit, but when we're talking about solar impacts, we assume that 0% of the modules will be manufactured in the US. And so now that we're getting solar module manufacturing in the US, we can, we would probably, if we were doing the analysis today and looking out into the future of when these would be built, raise that percentage up from 0. But at the time, we did not have the manufacturing support that we do now to have US manufacturing. Next slide. So we're going to look in terms of the economic impacts into 3 different buckets, and my apologies to Raj. I put the above ground transmission lines in here because it's what most people think of when they think of transmission, but I recognize that your project is unique and different in that. But the first impact is those on-site labor and professional services. Those are the construction impacts that Sue Green would employ, or their EPC contractor would employ to actually do the on-site work. So it's construction workers, engineers, others. The second impact, the indirect impacts, is the equipment production and supply chain impacts. You see that in number 2 on the right side of the screen. And then finally, we're looking at impacts, induced impacts, and those are caused by people having jobs and earnings in the first 2 categories, and they make just ordinary household purchases because they have income. So those would typically be, groceries, dining out, entertainment, and things. So those are those induced impacts. Next slide. So we estimated the cost of the transmission impacts as $3.3 billion, and with $2.7 billion of that sourced from within the U.S. Next slide. So here are the impacts. We've broken them out by the state of Illinois jobs, the state of Iowa jobs, and rest of the United States jobs, and then total, so that you can see where we got the total from. You'll notice that the state of Iowa jobs are larger, and the impacts are larger than state of Illinois. That's because of the line miles and other expected expenditures that are there. These are full-time equivalent jobs numbers. So these are looking at, you could think of this as a job year. And we're expecting a 3-year construction cycle. So these are saying what's the impact over those 3 years. If you wanted to get an annual average number, you just divide these numbers by 3 during the construction period. That's the first set of numbers, and it totals for the U.S. 22,804 over the Illinois, Iowa, and the rest of the United States. Operations jobs, these are ongoing impacts, and so the numbers are smaller, but they're expected to last the life of the project. And you get a total of 435, but again, that is over the life of the project. Next slide. We also estimated earnings, and I will say in terms of, I won't go through all the figures in terms of earnings, but just to say the construction impacts for direct and indirect are well-paying jobs. The induced impacts, even though those are large, will tend to be lower wage jobs because they will be in retail jobs, grocery store workers, waiters and waitresses at restaurants, things like that. And they're just in lower wage occupations. During operations, similar, direct, indirect are well-paying jobs. Induced tend to be a little less so. Next slide. We also estimate the economic output. Economic output is a measure like gross domestic product is. It's the value of goods and services for the economy. So we're looking at state of Illinois impacts, state of Iowa impacts, and then the rest of the United States. So almost $5 billion in economic output there during construction, and $192 billion ongoing during operations. I said that we also looked at the generation impacts, and so we were looking at what are the economic impacts of building the new generation, the wind and solar. But there's significant uncertainty in terms of their supply chain. So for a wind farm to be built in Iowa, where would the sourcing be, and where would we be in the United States in terms of being able to have domestic supply of turbine parts? I already mentioned solar and modules and where they're going to be sourced and how that's changed even in the last 12 to 18 months. And fortunately, these our estimates were conservative, and many of the adjusted numbers are increasing. But we wanted to take a range, especially on the wind turbine supply chain. So we did a kind of a low scenario and a high scenario for each of the turbine parts in the supply chain. So on the low end, the nacelle was 85%, towers were 55%, blades were 15%, and those are percentage manufactured in the U.S. And then for nacelle, the high scenario is 100% of the nacelles in the U.S., 70% of the towers, and 25% of the blades. You see the direct construction numbers, again, don't vary. This is really varying the high scenario and low scenario in terms of the supply chain impacts and where this gets sourced from. Not a tremendous amount of variation in those indirect numbers. You see somewhere between 23,611 and 25,422 under the indirect impacts for the low versus high scenario. But we did want to acknowledge the uncertainty in terms of where those supply chain parts would be coming from. And so you get a total employment then of between 45 and 48,000 from building all of the generation that will be unleashed by the transmission project. Next slide. So with that, in summary, our report shows that the Sue Green HVDC project will support 22,804 jobs during construction, another 435 during operations, 2.3 billion in earnings, 43 million during operations, 4.9 billion in output, and over $192 million in output from ongoing operations. And with that, I will turn it back to Raj.
Thank you, Dave. Yeah, what we'll jump into here is the societal impact specific to the delivery of the power. And so this was work actually that was conducted by PA Consulting, engineering, the PA Consulting group. And if you can jump to the next slide, overall, a quick summary of what power will be delivered. We're looking at energy source of 2 to 3 times the nameplate transmission capacity. About half of it will be wind, 30+% solar, and over 10% of battery energy storage, and resulting in a line utilization of annualized line utilization of approximately 70%. That translates to delivering 13,000 gigawatt hours or 13 terawatt hours of electricity into Plano, Illinois, in the PJM market. And of course, the goal there is to offset the power that would have otherwise been delivered by the fossil fuel plants that are slated for retirement by 2030. And if we look at the carbon footprint of that power that's currently being generated that will be retired and will be replaced by the power Sue Green delivers, we're talking close to 1 million tons of CO2 equivalent greenhouse gas emissions that will be avoided. And in terms of the permitting on the project, we are on track to obtain all the permits. The Army Corps of Engineers is the lead federal agency. Through them, we are working with the Fish and Wildlife Service and Illinois and Iowa DNRs, Illinois EPA on all the water-related permits. And the Corps, of course, deals with all the navigable waters and also the civil works permits. And then through them, consultation both on cultural resources related consultation and biological resource related consultation, both with the state historic preservation offices, the SHPOs, and historic agency in Illinois, and also the Fish and Wildlife Service and the DNRs. So if you go to the next slide, this is an overarching summary of the benefits that customers in the PJM market in Illinois will realize. As I said, we'll deliver about 13 terawatt hours of electricity per year. And these estimates here in terms of the quantitative value to Illinois communities are based on 25 years of operation, because that's what we base the economic impact on the Sioux Green transmission line operations itself that Dave was talking about earlier. Of course, keep in mind that they will continue to accrue. The project is expected to have a useful life of 60 to 80 years. So this is the summary slide. I'll get into a little bit more detail, but there are benefits to the electric grid, both from the reliability and resiliency point of view. And that is over $1 billion over the first 25 years of operation. And of course, the power will be delivered into Illinois to meet the power that needs to replace the fossil fuel plants, coal plants that are slated for retirement. And so this will be the Climate and Equitable Jobs Act that was passed in Illinois in September 2021. These are the power that will be delivered will be CEJA compliant power. And it will reduce the wholesale electricity costs that are currently prevalent in Illinois in this market. And over the 25 years of operations, that will result in over $19 billion in savings from a wholesale electricity price suppression point of view. And then there is customer savings that after all the costs of the transmission are rolled in and the delivered power, what the cost will be, and that the 13.5 billion in value to customers over the 25 years. And the CEJA delivered power that 19.3 billion. We'll get into the detail. That includes the cost of the power itself, the savings associated with capacity value, and also the REC value of the CEJA compliant RECs. And we already heard about the jobs and economics. This is basically a subset of the national figures that David presented earlier, which is looking at both construction and operations of the line itself, 4.8 billion, again, over the 25-year period. And last but not least is the environmental impact, both the social cost of carbon emissions that will be avoided and all the other air pollutants, and we'll get into some of those details. Ultimately, this is not to quantify it, but the qualitative aspect of it is the communities will benefit from the improved air quality and health outcomes. And most of the 19 plants that are slated for retirement, there are 19 coal-fired power plants slated for retirement by 2030 under the CEJA plan that are located primarily in disadvantaged communities. And so that is a very critical benefit that will be delivered in Illinois. So if you get to the next slide, we'll dive a little bit deeper. So what is the value that 19.3 billion that we talked about? And that basically, as I mentioned, falls in three buckets: the value of the energy, the value of the capacity market, and the value of the RECs. And the thing is, to meet the CEJA requirements, Illinois residents will have to pay for the energy capacity and the RECs associated with the electricity, whether Sioux Green is there or not. So, but this is the value of the energy capacity and RECs that will be delivered by Sioux Green into Illinois. So if you get into the next slide, that gets into the wholesale electricity price reductions associated with Sioux Green. Of course, this will change over time. What's shown here is on the figure there is a qualitative trend of for illustrative purposes on what the wholesale cost savings will be and how it will change over time. But clearly, customers pay for electricity based on the costliest dispatched power. That's how wholesale electric markets work. And as the more expensive fossil fuel fired power is retired, and is replaced by the wind and solar electricity that will be delivered from MISO Zone 3 into PJM, that will reduce the wholesale electricity price for the dispatch power within PJM. And of course, the variable cost associated with the wind and solar, there's no fuel cost, so that brings the wholesale cost down despite adding in the cost of the transmission to ship the power from Iowa to Illinois. So this is based on the power market modeling that was done by PA Consulting, and the overall value is over $13 billion over the 25 years. And if you get into the next slide, that talks about the environmental benefits and the value. Primarily, it's equally distributed between the social cost of carbon as defined by the EPA, and then the NOx, SOx, nitrous oxide, sulfur dioxide, and ammonia, particulate matter, and volatile organic carbon emissions. And these were all modeled again based on the power that is currently being generated, what will be retired, and what the quantitative value of that of the pollution is, and what the associated health benefits and life saved are, again based on EPA's COBRA model. So these are all based on EPA estimates from 2022 on what the value per unit of emissions reduction, whether it is greenhouse gas emissions and CO2 equivalents, or other air pollutant, harmful air pollutant emissions that are causing health effects in the communities that these fossil fuel plants are currently operating in. So that's those are that's a deeper dive into the numbers that I presented in the first slide. And I believe at this point we'll hand it over. If you go to the next slide, we'll hand it over to Chris to talk about the downstream economic impact of delivering the power to new and growing users in Illinois.
Thanks, Raj, and I'll give Chris a quick intro. Chris is economic analyst for SER and assists with the production of the economic impact studies, including sourcing, analyzing, and graphing government data, and performing property tax analysis for wind, solar, and transmission projects. Thanken has a Bachelor of Science degree in Sustainable and Renewable Energy and minored in economics. Chris?
Thank you, Ethan, and hello to everyone. Thank you for being with us today. I'd like to talk to you about this really unique and novel analysis that we did for Sioux Green. We were attempting to quantify the economic impacts as a result of the transmission line to the Illinois business environment. This is a very unique and novel analysis that we've actually never done before, but I'd like to share with you the methodology, justification, and results that we actually looked at. So first of all, we need to justify why businesses would be attracted. So next slide, please. And admittedly, it's pretty easy to do. Large companies want renewable energy. This is a graph from the 2022 American Clean Power Report about clean power powering American businesses. It shows renewable energy procurement from 2010 to 2022, and you can see that it's been skyrocketing in the last few years. The graph shows 326 companies have purchased 77 gigawatts worth of clean energy since 2010. I'd also like to read a quote from a Burns and McDonnell white paper that they wrote about site selection. So not just any form of energy will do for today's industrial end users. Increasing numbers of companies are seeking energy solutions that support their corporate sustainability and net neutrality goals as expressed in their environmental, social, and governance policies, and pledges committing to 100% renewable energy by 2050. So next slide. Again. Yep. So with that in mind, and the idea that more transmission lines equal greater access to renewable energy, and the fact that the Sioux Green transmission line terminates near Chicago, Illinois, all these reasons culminate into the reasonable assumption that new businesses will be attracted to Illinois due to Sioux Green. Next slide. So how do we choose which industry to focus on for our report? Well, we looked at about 516 different industries within Illinois, and we looked at their electricity spending from 2013 to 2022. We used InPlan, which is our economic modeling software, and we used their location quotient data. Essentially, is the concentration of the industry within the state of Illinois larger than the national average? Is it less than the national average? And between the electricity data and the location quotient data, we analyzed those points through a shift share analysis. essentially, has the industry grown within the state of Illinois according to expected projections? After doing that, we were able to filter and get a decent list, about a dozen different industries that we sorted into a SWOT framework. So the strengths and opportunities were industries that were of a large concentration within the state of Illinois and have been growing larger than the industry average would expect the industry to grow, and the national average. So after going through those dozens of industries, we finally selected data centers. Again, data centers had the largest competitive advantage within the state of Illinois within our research, and they had some other reasons for being selected. Notably, their huge power demands. You know, data centers may look like a warehouse or just a simple office building, but they have the power demand of a large manufacturing plant. Also, data center companies and the companies that operate data centers have a strong interest in using renewable energy for their power demands. And within the state of Illinois, data centers have a huge presence, specifically within the Chicagoland area. Chicago is the second largest data center market within the United States and fifth largest in the entire world. And they are just going to continue to grow despite power constraints that actually afflict the area. They have been growing decently every single year. Another key point is the evolution of computing, whether it be through cloud computing and artificial intelligence, which again use a lot of different power, and with the rise of quantum computing. This is especially important in the state of Illinois. Governor J.B. Pritzker has asked the Illinois legislature to invest hundreds of millions of dollars over the last few years in developing the quantum computing energy industry so that it goes from the laboratory setting, which it is now, into a full-blown mature energy. Governor J.B. Pritzker wishes for Illinois to be the Silicon Valley of quantum computing, and that's going to require a lot of power. I'm not going to get into the details and the engineering of quantum computing, but essentially they have to operate at temperatures near absolute zero, so 0 degrees Kelvin or negative 459 degrees Fahrenheit, which is not an easy temperature to get anywhere near or even achieve, and is going to require a lot of power. So all these different reasons culminate into the idea that data centers are going to benefit very largely from a new transmission line being built within the state of Illinois. So next slide. So we are projecting decades into the future, and there's uncertainty with that. So what we decided to do was create a low and a high scenario. For the low scenario, we looked at it from the tax incentive. The main driver was the tax incentives that state of Illinois has passed. So if you invest $250 million, you get tax incentives from the state of Illinois. So we use that as the foundation for our low growth scenario. This equates to about 456 megawatts worth of data centers being put online between 2028 and 2042, which represents about a 30% increase in the expected 2030 data center capacity for Chicago, which we conservatively assume at about 1.5 to 2 gigawatts worth of data centers. This is based on estimates from JLL, Cushman and Wakefield, and CRBE industry reports about data centers within the city of Chicago. We also started in 2028 because we assumed some companies would want to build early in order to utilize Sioux Green when it's operational starting in 2030. We also assumed that building efficiency numbers would increase as a result. So if you're constructing a data center, the amount of dollars you spend to build 1 megawatt will slowly decrease over time as we get better at building data centers. For the high growth scenario, we went a lot higher than that. We looked at about $544 million to $722 million in annual investment, or about 1.1 gigawatts worth of new data centers. This represents about a 76% increase in the expected 2030 Chicago data center capacity. And the modeling for that was about $3.7 billion in construction costs. The actual total cost for the data centers in both scenarios will be a lot higher, but we actually want to just focus on the costs that will be staying within the state of Illinois. Racks, servers, other sort of specialized electrical equipment we assume will be procured outside of the study region of the state of Illinois. Therefore, they were not included in our construction modeling. So let's look at the results next. So for the construction side, on the low side, A low scenario, we're looking at about a 20,000 jobs supported during the construction period. About 13,000 of those will be the direct construction worker jobs. The difference between the total and the direct jobs are those indirect and induced jobs that Dave mentioned earlier. If you're interested in a more detailed explanation, I highly suggest you go to our Strategic Economic Research YouTube page and watch our permitting webinar, where we go into a lot more in depth about the differences between direct, indirect, and induced jobs. But on the low side, we're looking at about $1.4 billion in labor income supported during those construction of those data centers, with about $3 billion in output added to the state of Illinois. Now, on the high side, as you expect, a lot higher, almost 52,000 jobs supported during the construction period, with about 33,000 of those being the actual construction workers. The 52,000 total jobs supported will earn about $3.6 billion in labor income and contribute to the Illinois GDP of about $8.2 billion. Next slide. But so previously we just looked at the construction impact, but these are the actual operations of the data centers during the 2028 to 2042 timeframe. On the low, but we also looked at the operations side as well. So on the low side, we're looking at about a little under 2,000 total jobs supported during the operations of the data centers, with about 347 of them being the actual data center workers, of specialists and technicians, and the managers that are actually in the centers. The total 1,900 total jobs will be earning about $192 million worth of labor income during that time, and contributing to the Illinois GDP of about $633 million. On the high side, we're looking at about a little under 5,000 total jobs supported during data center operations, with about 867 of those workers being in the actual data centers. And they'll be contributing to about $1.5 billion in Illinois GDP. Next slide, please. So what we just looked at was the 2028 to 2042 impacts. And the reason we chose that time frame is because Sue Green will actually have this utility bill increase during that time. And we made the assumption that data centers and the companies that build them and operate them will be wanting renewable energy so much that they'll be willing to pay that extra premium in order to build them within the Chicagoland area. Again, second largest in the country. But post 2042, Sue Green will have this increasing reduction in Illinois utility bills. And that's going to open up a lot more economic activity as a result of those electricity price savings. So now we have to kind of shift our analysis to include more industries that are going to be incentivized to grow and expand within the state of Illinois. So next slide. So we added two more industries to our analysis for the remaining study period from 2043 to 2050. These were other industries that were not selected initially, but have a large presence within the state of Illinois and have been actively growing within the past decade. So we're going to assume that that growth is going to continue for decades to come. So the other industries that we included were pharmaceutical preparation manufacturing and miscellaneous product manufacturing. We utilized Bureau of Labor Statistics data as well as in-plan data to help project a baseline forecast to the year 2050 of projected growth. And then we used elasticity data from the Advanced Energy Economy report that we based a lot of our methodology on. They created a report looking at the creation of a Western RTO and the economic results that will happen for that. We borrowed a lot of methodology from them. So a big shout out to them for creating a really nice report for which we could use. So in our report, we were able to use elasticities to project out what the additional growth would be for data centers and their other industries. So for the low scenario, we used an elasticity of -1.3. This essentially means that for every 1% reduction in electricity prices, there would be a 1.3% increase in job growth for the selected industries. On the high side, we used -3 as our elasticity. Again, a 1% decrease in electricity prices would result in a 3% increase in job growth. And we did this from 2043 to 2050, and then we subtracted the additional job growth. We subtracted the baseline from the additional job growth to get the growth associated and attributable just to Sue Green. So on the data center side and the low growth scenario, we're looking at about a 4,200 job increase by 2050 from the baseline. And then on the high side, a lot higher, about 26,000 jobs growth. The total of all the different industries was about 15,000 jobs created as attributable to Sue Green by 2050, with about 77,000 jobs created in the high growth scenario that are attributable to Sue Green. So next slide, please. So if we take the 2028 to 2042 impacts, and then we add them together with the 2043 to 2050 impacts, we get the total operations results from all the different modeling that we did. So on the low end side, we're looking at about 62,000 jobs supported, with about 16,000 of those being the actual operations from main data centers, but the other pharmaceutical preparation manufacturing and plastic product manufacturing. They'll be earning about $6.8 billion during their operational periods and contributing about $26 billion to output. And then on the high side, noticeably higher amounts, 316,000 jobs that are supported during this time frame, with about 78,000 being the direct jobs. They'll earn about $34 billion with about $131 billion of output to the state of Illinois. Now, these are very large numbers, but you have to keep in mind that we were talking about 22 years worth of impacts, and they're happening to industries that are currently experiencing large amounts of growth and that have very steep trajectories for the next several decades to come. And they're occurring within a very populous state and a populous area being Chicago. When you have impacts and economic activity occurring in larger population areas, they yield bigger impacts. The other thing to point out is that this actually doesn't even take into account the additional property taxes, which also create additional impacts within community governments and local counties. And we weren't able to get any construction impacts. But again, if you're dealing with massive amounts of data centers and manufacturing plants, they're going to have very, very large construction impacts as well. Right now, what you're seeing are just the operation side. So that's it for the pertinent part. Next slide. I just want to give a quick plug for the Illinois Renewable Energy Conference that SCR is hosting in October. It's on October 1st and 2nd, which is a Tuesday and Wednesday in Normal, Illinois, which is essentially Illinois State University's campus. So please head on over to illinoisrenewable.com to register or sponsor. This is our second year of hosting it. We'll have we're expecting about 300 plus attendees, 40 plus speakers. So if you're interested in Midwestern energy policy, please come on by. And I will turn it back to Ethan now. Thanks, y'all.
Thanks, Chris. Yeah, if there's interest from anyone here to attend the Renewable Energy Conference in Illinois, it would be great to meet you in person. So I'll be there, and Raj and Dave and Chris. So feel free to register, get your registration in before cost goes up. We'll be moving into our Q&A portion of the webinar. Looks like we've had a few questions trickle in here. Let's see. And Dave and Raj, if you're able to see the questions on your end too, feel free to pick and choose one that interests you. Someone did ask, can we find more info online on the business attraction justification? Very interesting.
So, I mean, that just culminated from all the research we did when constructing our report. I just went over the main highlights. Essentially, businesses want renewable energy. That was a conclusion we drew from the American Clean Power Report. Very convincing that over the last few years, they've been purchased over 77 gigawatts worth of operating and contracted clean energy to reduce their carbon footprints and hedge against electricity prices. The other notable thing is that the state of Illinois is offering these big grants for certain industries that they're focusing on, like advanced manufacturing, agribusinesses, biotechnology, et cetera, quantum computing, like I mentioned, and the fact that and the fact that Illinois has the Chicago metropolitan area is one of the larger areas in the country, boasting a huge number of businesses that are a huge number of like large businesses that mainly data centers wish to co-locate near to better serve.
This might be an interesting one, and the question came up: how about these data centers stop requiring so much power and design their systems to require less power and generate less heat? So the risk in terms of our analysis and forecast would be that the demand for electricity levels off from data centers, or for that matter, any of the other businesses, but in particular for data centers, with the technological change, could there be a reduction in in demand from those data centers? Raj, do you have any thoughts on that?
And clearly, like every other industry, particularly because they're such a electricity intensive industry, they're doing there's constant innovation going on to reduce the cost of operations, because it is basically everything that they save there will basically translate into increased profits for them. So that work is going on, and to the extent that the physics and engineering aspects of it will allow that we will continue to see improvements in energy efficiency in the space, just like we are going to see in other industries. So definitely, but the question still, the fact still remains that artificial intelligence, quantum computing is all bringing in an order of magnitude increase in power demand, that irrespective of how efficient they get, it's still going to be multiples of current installed power capacity that will be required a decade or further from now. So that part of the equation in terms of significant increase in power demand. And also we have to keep in mind that it's not just data centers, right? There is the baseline power electricity use. There's a lot of beneficial electrification going on for thermal needs in residential and commercial space, both for space heating and with again, to Dave, to your point of efficiency, with the heat pumps, air source heat pumps, and reducing, and the hybrid systems even for hot water in residential and commercial space, which is translating into displacing natural gas use and replacing it with electricity use. That's another area of increasing projected demand for electricity. And lastly, there is transportation. There is total cost of ownership of electric vehicles continue to drop, and the battery manufacturing for EVs also continues to drop. So there's going to be increased electrification of the transportation sector for personal vehicles for sure, but also there's a lot of effort underway, particularly in the upper Midwest, on electrification of buses for local transit. So there's a lot more beyond data centers where the baseline electricity use is going to continue to grow. And there is another question here about rooftop solar, which is a very valid question to ask. It's always a trade-off between transmission and distribution versus distributed generation. And the fact we have to keep in mind is even in residential, if you look at energy use intensity of occupied space, there is if it's a single family home, yes, there is enough roof space available for rooftop solar to meet the demands. But the minute you get into multifamily housing, you right there, you don't have enough roof space available to meet the demand for all the occupied space. And then expand that into something like the electricity use intensity of data centers. It's just totally out of the question that distributed generation with rooftop solar can meet that. And also there was a question about the solar installation on farm property. It's a question that's always it's a question that farmers have grappled with. And clearly, we're not talking about just solar here. We're talking about solar and wind. And if you look at wind and even solar, if you look at overall renewable energy, is basically viewed as a cash crop by agriculture, by farmers, that for a small portion of their productive agricultural land set aside for solar and wind generation, generating as much or more in terms of operating margin and profits for them as the rest of the agricultural output is. And clearly, there are larger questions at a macroeconomic scale to be answered about food security and all aspects of that. But clearly, what we're talking about here, mostly from North Central and Western Iowa, is predominantly wind and wind power. Set aside 5 to 10% of your farmland and generate as much or more revenue from that as the remaining 90 to 95% of your agricultural products are generating for the farmers. So it's again an economic play, and it has played out over the decades, and the levelized cost of generation for wind and solar continue to drop, which means that there is even more money at play in terms of what is the value for farmers here for hosting these renewable energy generation facilities on their properties.
Yeah, I think to emphasize the point that you made in your slides, you look at the wind speeds, and I think people, who aren't familiar with wind energy lose the fact that wind speed is such a critical input, and where those projects that can reach your termination point for Sioux Green have much lower cost of operation. The power generation is a cubic function of the wind speed, and so if you double the wind speed versus if you say, well, just put it at the termination point in Illinois versus putting it in Iowa, you can, if you double the wind speed, you get 8 times the generation output. And then that lowers your cost with the same technology, same turbines and things. So it really is, beneficial to unlock those resources.
Exactly. And again, also the question of population density, right? What we have population density where these data centers and all this electricity demand we're talking about in Illinois is quite different from population density. So it's a combination of, is the land available? What is the cost of the land? And what is the wind speed? And particularly the wind speed becomes even more important today than it was a decade ago, because now we have turbines that are located 80 meters above ground wind speed, as opposed to much lower level and larger turbines. And the wind speed is, of course, higher as you get farther away from the ground. And so the difference in terms of levelized cost of generation between Western and North Central Iowa and Illinois becomes even more significant with these taller turbines.
Well, great. I think that wraps it up. Thank you, Raj and Dave and Chris, for your presentations, and thanks everyone for joining us. I will be emailing out the recording when it is available, so please feel free to share that. It'll be on our YouTube page as well, along with other webinars that we've done in previous months. So thanks again.
Thank you, Ethan.
Thank you.
Thank you, everyone.